So basically, based on the stability of carbocation, we can say this position is the best stabilized carbocation in the given scenario. Let's go to the next question. HgOAc twice H2O. Okay, I remember we discussed this in the class also, that if you make oxymercuration demercuration, first a mercurium bridge will come here and water will attack on this side. Okay, and bond will break and finally H minus will come on this side. So if I write it in the product form, so we have like this methyl and OH here and hydrogen here. Got it? So what is necessary is that OH and H could be non-stereospecific. That means they can be both on the same side or opposite side. It does not make any difference. So first option is wrong because OH is added here. Second option, there is no OH added. Third option, OH is added, but here it is wrong. There is no CH3 here. Fourth option is correct. This option makes more sense. Then next question. Major product of the following reaction is, okay. So check out when you have HI what we shall do here. Okay. See first here we have double bond and we have iodide here. Okay. First thing what we do is add H plus here and positive charge here. You might wonder, sir, this is withdrawing group. Why do we add this? Reason being the lone pair on iodide will always help in getting conjugated like this. This is sigma conjugation. Okay. And once you get this, I minus will attack. The next I minus will attack here. That converts into vicinal iodides. And you notice that vicinal iodides are highly unstable, so that will form a propene. And eventually, propene, when you again react with HI, following Markovnikov's, it makes a isopropyl iodide. Okay, so this is the final product, which is option B. Okay, so let me revise again. On a double bond, first you make a Markovnikov addition, you get a positive charge. That positive charge is stabilized by the sigma resonance of iodide. And thereafter, I minus will attack here, making into vicinal iodides. Vicinal iodides are extremely unstable, that will convert into a double bond. And thereafter, again, HI is added. So finally, you'll get isopropyl iodide. See the next question. Which of the following reactions result in the formation of pair of diastereomers? Okay. So in the first case, if you notice that we have methyl and methyl, and Br first carbocation will be forming on this position, and then okay, then methyl will shift here. So then positive charge will come here by migration, and thereafter the bromine will come here. Okay. So you would actually notice only one carbocation present. Okay. So in this case, first carbocation will form here. Furthermore, there is no migration because it is already at secondary position, and this is methyl given, correct? So in that case, we will have methyl here and then bromine here. Because bromine added is forming a chiral center, and this chiral center is a fixed chiral center, you would have either RS or RR type of isomers, which is nothing but diastereomers. Done. So this is the pair of diastereomers. Okay. So second thing, if you notice, HBr, this is an anti-Markovnikov addition. So you will have Br being added here. Methyl is fixed here. So only one enantiomer is forming. Here, when you have OH and methyl here also only one enantiomer is forming due to anti-Markovnikov addition. So only B is correct. Okay. Next. Notice here a hydrocarbon X is found to have molar mass 80, a 10 mg of hydrocarbon X on hydrogenation consumes 8.4 ml of H2 gas. Okay. Uh, 8.4 ml of H2 gas. And X on reaction with 1 mole of Br2 gives a dibromo derivative. Okay. So basically, X has a double bond. That is what it is telling us. Correct. It is a double bond which has molar mass 80 here, correct? and 10 milligrams of hydrocarbon X on hydrogenation will consume this much amount. Okay. So you can start with the basic pi bonds here, correct? So first thing what is asked is the number of double bonds present in hydrocarbon P. Okay. Sorry, one second. Where is P here? I think it must have been X. That was slightly mistaken there. So hydrocarbon X is found to be a molar mass, uh, this much. Okay. P. Okay. Now listen up. This could have been multiple bonds here because if, well, this is X here, correct? Now, this might be consuming 1 mole or 2 moles here, right? So this might be consuming 1 mole or 2 moles. So we do not know that. And but X is definitely reacting with 1 mole of bromine here. So this is also a chance, right? So in that case, what we can think about is, we might have only one pi bond here, like this, maybe something like this here, or something like this here. This is one pi bond here, or it could be in an open chain also like this. Okay, maybe like this. So check out whichever is coming molar mass closer to 80. Got it? If you want molar mass closer to 80 means we should have at least 5 carbons here. Correct. So you know that, for example, if you have C5 here, H10 is what we usually have. Correct. So 12 5 is a 60 plus 10, so that makes it 70. So maybe we can have 6 carbons here, right? So 6 carbons, that makes it 72 as carbons. And we need to have how many? Only 8. So that means we must have some kind of a double bond here. So if you notice here, we have 2, 4, 5, 6, right? Sorry, 2, 4, 5, 6, 2, 4, 5, 6. Okay. 6 here. So 72 and 6, 78, which is still very closer values here. So something of this kind you can think about. Okay. That means we should have one more double bond. So probably they, because you're only consuming, check this out here. X on reaction with 1 mole of Br2 gives dibromo derivative. Okay. So which means it could have been two pi bonds also. It is not necessary that I need to have only one pi bond. So yes. So these are all the options which are matching. So we need to have 6 carbons, right? So I could have it like this with a double bond here, with one more double bond here. I could have 5 carbons with one methyl here, maybe double bond at any position. This is also matching. So this is a kind of molecules which are matching here. Okay, so one more pi bond, correct? So now number of double bonds present in the hydrocarbon, how many we can have? Minimum we can have is 2. Okay, so therefore it can be uh, 2 double bonds divided by 2, so which is 1.5. Okay, so that will be the answer, correct? So we could make this a cyclic also, by the way. For example, if you have like this, correct? What if I make this into a cyclic form and then double bond here? This is also a possibility. That's why multiple keys were given. But I would suggest go for 1.5, which is more appropriate because these are less stable cases. Okay. Next, calculate the amount of dibromo derivative form when 40 grams of hydrocarbon is made to react with Br2 if the yield percentage is only 75. Okay. So molar mass, I mean, if you take 40 means half a mole. Okay. So half a mole means, suppose if I consider this as your original molecule, okay, its reactivity is 2 moles of Br2 in the presence of CCl4. That would make it bromine to add at all positions here. Br and Br here, Br and Br here. Correct? So here we take 0.5 moles because molar mass of molecule here is 80. So therefore 40 means 0.5 moles. So you can see for 0.5 moles how much it is required. 1 mole requires 2 moles. So 0.5 requires 1 moles. So 1 mole of bromine is required, everybody. Clear? But the yield is only 75%. Okay. Calculate the dibromo derivative form when, oh, sorry. We need to only make dibromo, not tetrabromo. Sorry, my mistake. So I need to make this one double bond has to stay. We need to make only one brom. So we will still be using, in that case, zero point 0.5 requires only 0.5 moles. So zero point 0.5 moles of bromine is required. Okay. So that also makes this as zero point 0.5 moles of the product form. So what will be the product value here? So molar mass of this is 80, and 80 plus 80 plus 80. So 83 is 240. So 240 is the total molar mass of this molecule. So half of it is the weight of product. So half of product is 0 0.5 into 240, 120. Okay. That would be the case. Clear? Everybody, please check if you have doubt. Yeah, sorry. Another thing is I need to take only 0.75 percentage that I forgot to multiply. So which makes it 90 grams because the yield is only 75 percentage. Okay. So please relate with this question, everybody. If you have any doubt, you can ask me. If you don't have source for mic, please write it in your books. What is your doubt? Okay. Once I'm there, I'll be discussing with you guys. Okay. See the next one here. This is Hoffman exhaustive elimination. So first methylation is being done here. So that converts the product molecule into this form with plus ammonium salt. With Ag2 or AgOH, it will go for elimination. And we discussed this. We need to first figure out what are the alpha and beta position. We need to notice which is more stable beta position. So therefore, this side the bond breaking would happen. The bond would break here. Base in this case OH minus will come and extract here. So that makes it lone pair here and a double bond here. Correct. So this is the 3-degree amine and this is the alkene which you have. Okay. So if B contains P number of carbon atoms, so number of carbon atoms is 2. So P is 2. And Q number of hydrogen atoms. So Q is 4. Then 2 by 4. So 2 by 4 is 0.5. Done. Next. Double bond. This is exhaustive Hoffman exhaustive methylation. HEM means Hoffman exhaustive methylation. And is asking us to do it 2 times. So 2 times in a sense that first you would already we have a plus charge here, so we will take this as Ag with OH minus here, with OH minus the beta position is here and alpha position is here, the bond will break and that will make the molecule to get a double bond here. Okay. And nitrogen is connected with 2 methyl groups. And if you have to do one more time exhaustive methylation one more time, so one more methyl will come, plus charge will come, and second time OH minus will again attack on this beta position, bond will break here. So by doing that, the product what you will get here is like this. This is the double bond, and nitrogen would have 3 methyl groups and a lone pair. So these are the final products formed. Okay. So N, Me thrice, and alkene is like this. Okay. Pentadiene. Okay. If the molar mass of the alkene is R, then R by 10. Okay. So 5 carbons, correct? So we have 60 plus. So if we have 5 carbons, normally imagine if you have to be having an alkene. If it is alkene, it is supposed to be 12, right? So which makes it 72. So subtract 4 out of it. So 68. So it is going to be 68 by 10. So 6.8. Done. Here, molar mass is 72. I mean 68. 68 by 10 is 6.80. Next. Alkenes can exhibit geometrical isomerism if the groups attached to the double bond are different. Okay. A hydrocarbon with a molecular formula, this can show X number of structural isomers, only open chains, and Y number of stereoisomers, only geometrical in open chain. So then how many we can get? So let me write down C5H8. So you can clearly notice that there are two pi bonds here. Okay. So because there are two pi bonds, so I can say that the first in open chain here like this 1, 2, 3, 4, 5. So I can put one double bond here and double bond here. I can put one double bond here and one double bond here. One double bond here and one double bond here. This way, isolated form. Okay. Or we can also put one double bond here and one double bond here. This way. Okay. And thereafter, we can also have triple bonds. So one triple bond here and one triple bond here. These are possible with straight chains. Got it? So just put it down here. You can see. These are all possible forms. And everything I'm keeping it in open chain only. Okay. And we can now have branching of it. So if at all I make the branching of it here like this way. 1, 2, 3, 4. So now I can put double bond here and double bond here. This is one existence. I can keep double bond here and double bond here. Okay. And that's it. These are the only two double bond forms. Next, triple bond. Triple bond, only one is possible, that is this one. Okay. So these are all the possibilities of the isomers. Okay. Structural isomers. Now, Y number of stereoisomers, only geometrical in open chain. So we need to only count the geometrical forms. So if you count the geometrical forms here, so this is the geometrical form. So two here, two geometrical isomers. And then we have nowhere else. That's it. Check out. That is the only position where we can have the geometrical isomers. No other chance. Okay. Now, can we have a structure like this 1, 2, 3, sorry, 1, 2, 3, 4, 5 here, like a tertibutane, 1, 2, 3, 4, 5. Or you can have 4 here, 1, 2, 3, and in any direction you write, again you'll get the same thing. But problem with this case is you cannot accommodate any double bonds on it. So this is not possible. The neo kind is not possible. So only this is possible form here. Okay. Clear? So check out. So how many structural isomers we are getting, everybody? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we totally got 9 structural isomers minus 1 by Y. Y is the total number of stereoisomers. Only geometrical in open chain we have to consider. Okay. So how many stereoisomers I'm getting? Only 2. Because rest all are not geometrical isomers. Okay. Everywhere we can see there would be either optical isomers or no isomers. Okay. So only 2 here. Correct? So check out how much we are getting. 4. Please check, everybody. Any doubt? Next, check out 29. Out of the following alkenes, X number of alkenes can perform or give exhibit geometrical isomer. Y number of alkenes cannot exhibit geometrical isomers. So let's start with the first one. Okay. So this one is Y because it cannot perform geometrical isomers. This one is also Y, cannot perform geometrical isomers. This one is also Y, it cannot perform geometrical isomers for the reason that these two groups are same. This one is X, which performs geometrical isomers. This one is also X because methyl can make geometrical isomers here. This one is also X because it can perform geometrical isomers. This one is Y, it does not perform geometrical. This one is also Y, does not perform geometrical isomers. So how much is the x we got? 1, 2, 3. So x value is 3. That means 3x molecules are there. Y. So 1, 2, 3, 4, 5. So y is 5 here. Correct? So how much we're getting? 0.6. Everybody clear on that? Next. This is a standard question. We discussed this last time. So every time you see this, directly option, go for option benzene. You don't have to think so much. Okay. But I also told you that the product A cannot be. Okay. Which means, will it be this one, or this one? No. So that means you opt these options. Okay. Correct. Next. Which of the following reactions 1,3-butadiene will be obtained as a major product? Okay. So check out on the third butoxide form here. So third butoxide can extract H plus from here, H plus from here. You can get double bond and double bond. So no problem there. You'll get this product. So A is correct. Concentrated H2SO4, correct. You can make this as OH2 here, OH2 here, and because it is at primary position, E2 is favorable. So H will go from here, H will go from here. So this case also we can get double bond. Okay. And P2 catalyst, nickel borate is P2 catalyst. It will only reduce the triple bond. It does not touch the double bond. So hence, that is also going to give you the same product. So these two are okay. Alcoholic KOH. So it can take Br here, H here, make a double bond. Br here and H here, and it can make a double bond here. Correct. So what do we get here? So 1, 2, 3, 4, 5. So we have 5 carbons here. So that makes it double bond at this position and this position like this. So there is a conjugated form present, but it is not exactly 1,3-butadiene. So answer is ABC. Addition of HCl, HBr in the presence of peroxide and major product obtained is anti-Markovnikov. Okay. We know that addition of only HBr works, HCl does not work. So A is incorrect. Okay. Next, addition of Br2 to Z-but2ene gives RR and SS dibromobutanes. Okay. So let me tell you, Z means cis. Okay. So we have like this cis form. And cis form when you react with Br2 here. Correct. So as you react with Br2 here, so we will end up getting this as, what is the form? You know that Br is going to make an anti-addition. This is a cis molecule. So the product we should get is 3O. 3O like this. Okay. And remember that when you have 3O group, the configuration above and below will be same. If this is S, this will also be S. Okay. And likely, if you have Br here and Br here, methyl and methyl, H and H, the same thing will follow. If this is R and this is R, this is the product formation. Okay. So yes, both will be 50-50 percentage and racemic mixture. So B is correct. Acid catalyze hydration of 2-phenyl propene gives 2-phenyl 2-propanol. Okay. So 2-phenyl propanol, 2-phenyl propene is like this. This is pH. And acid catalyze means carbocation will come at this position, which is more stable. After that, we have to add alcohol, which is 2-phenyl 2-propanol only. So this C option is also correct. Burge reduction of 2-butane gives trans 2-butane. That is correct. Right. So B, C, D. 33. Which of the following is not a major product of the following reaction shown? Okay. Br2 and water. Now listen up carefully. When you have Br2 water, you can have Br minus and water. Both will act like nucleophiles. Okay. Both are nucleophiles. But electrophile is only one, which is Br plus. Br plus is the only one which is acting like an electrophile. And you know that electrophile gets added here and nucleophile will come at this position. And both should be opposite to each other. So that means if Br is coming outward, so here in this case, Br should be inside. Similarly, if Br is coming outward, then OH could be inside. Because water is in large quantity, this is the major product that you will report. This is major product. Okay. Clear, guys? So check out which options are matching more here, which is not the major product. Okay, so let's see which are all not the major product. Br and oh. Okay, so will this come? Okay, yes, will it might come. Anti-Markovnikov addition would happen, but to a very small extent. Okay, next. Second one, sin. Sin can come here. Sin can come here, but again, it is a very, very minor product. C. Can OH come on this position with opposite form? It can, but it is a minor product. The only major product given is D. So D is the only one which is major. Rest all are minor or in traces. They're either minor or they are in traces. Okay. Next. 3-bromocyclopentene reacts with Br2 or Cl2 to form two products. Y is not optically active. Which what cannot be structure of Y? What cannot be structure of Y? Okay. And you see Y is not optically active, which means it should not be. It should be mesoform. Y is a mesoform. So which cannot be Y? Out of this, which cannot be Y here? You can see this is mesoform. Okay, this one is not mesoform. So B. This one is a mesoform. So this is Y. And this one is also mesoform. So this is not either. So these cannot be the cases. So we will have only. Oh, sorry. I made one mistake also. One mistake is because you cannot have a sin addition here, right? So even A cannot happen because Br2 is an anti-addition. So both Br on the same side cannot come. Okay. So C can come here, right? Because this Br and Br is on the opposite side. Got it? And D also cannot come. So answer should be ABD. Please check quickly. Right. Notice the next one. Next reaction is if you have a trans molecule, add Br2. We know that when it comes to trans molecule, what do I get? I will get this as A will be, and trans plus anti will give you erythro. So Br and Br will be on the same side. pH here, and hydrogen here. So this is the A product. Then you are performing 2 moles of NaNH2. So that means you will get an elimination product. So we will have phenyl here with triple bond. And then you are making H2 to add. So it is a Lindlar's catalyst. So which make a syn addition, which converts into an alkene. C, this one is correct. And for A, this one is correct. Okay. B, this one is correct. So B, C, D. Please check. Next. X number of transition state and Y number of intermediates. I remember we kind of did a similar type of question. Check out here. If you have this way, we have to get an alcohol, means first you have to add H here and positive charge will come here. Correct? This will go for ring expansion. Okay. So you will break the bond here, push into 5-membered ring. So as it forms a 5-membered ring here, correct, you will have a methyl on it, and adjacent to that is also a methyl on it. Sorry. And that will have a positive charge on it. Okay. So that will have a positive charge on it. And hereafter, there is no more migration. So directly OH2 plus addition will happen, hydrolysis. And that will finally lose out H plus to give the final product, which is OH and this one. Okay, this is the product which you get. So this is intermediate 1, this is intermediate 2, this is intermediate 3. Okay, So 3 intermediate, which makes it 4 transition states. So answer should be 7. Okay. Next 37. If this compound is treated with palladium carbide in excess of hydrogen, how many stereoisomers of the product will be obtained? Okay. So basically we need to convert everything into an alkane form here. So you'll have an ethyl here. We will have an ethyl here this way. Correct. So since these two ethyls are at chiral centers, two will be enantiomers, one will be mesoform. So one will have a plane of symmetry like this. So answer is 3. Number of olefin of C4H8 is X and number of Markovnikov addition in the stereoisomers is Y. Okay. In C4H8, correct. So H8 means we have only one pi bond, correct. Olefins means we need to have a double bonds. So therefore 1, 2, 3, 4 a double bond here. 1, 2, 3, 4 double bond here, correct. So this will have cis plus trans both. But here there is uh, uh, no Markovnikov addition followed because they are symmetrical. Here Markovnikov is followed. Okay. So number of Markovnikov of products including stereoisomers is okay. So if in case if you have Markovnikov addition followed, this is the product what you will get. Okay. Right. So now, acha, in the first case, what if I have to make an addition in this case here? So in this case, we can have a Br here as well because H plus will get added. Br will come at this position. So only this product you will get. Okay. Now what is the other olefin I can get? I can get a double bond like this. Here also I can have a Markovnikov addition. So we can have a Br value here. So here we'll get two products. Here I'll get one product. So using Markovnikov, I'll get three products here. And total number of products of X will be equal to, this is 1. Here there are cis and trans 2 and here it is 1. So total 4. So question asked is X plus Y. So 4 plus 3 is 7. Everybody got that? Right, everyone. Let's go to the next assignment quickly. Day 1, assignment 2. Check 19th one. How many of the following statements are correct about the following reaction sequence? 3-methyl 1-butene. Let me write the structure. So we have 1 butene and 3-methyl here. On adding with water, what do I get? First you will get a Markovnikov addition. So carbocation will come here. Positive charge will migrate and eventually water will come here. So this is the product. While on the other hand, when you take oxymercuration, demercuration, you will get no carbocation but Markovnikov addition. On this position, it is anti-Markovnikov addition. This is the product form. Okay. So notice Y is optically inactive due to external compensation, which is true. Okay. That is true because here we will have star here. That means it will be a chiral center, but 50-50% chances are there. So 50-50% means it will become racemic mixture. So this will be plus and minus. So racemic mixture is inactive due to external compensation. Keep that in mind. While meso is inactive because of internal compensation. X and Z are optically inactive. Consider major product in this case. So major product is this one and consider major product in this one. So these two are optically inactive. That is also true. There is no chiral center on it. X and Z are optically active. So that is incorrect. X is optically active, but Z is optically inactive. So that is also incorrect. So only 1 and 2. Okay. So how many statements correct? Two statements are correct. How many of the following reagents attack the alkene via syn addition? Okay. How many of the reagents make syn addition? You know that this is an anti-addition. This is a syn addition. This is an anti-addition. Right? This is a syn addition. This is an anti-addition. Again, how many? Two. Next, HBr peroxide form. Okay, if you have HBr peroxide form here, so basically we have a double bond here like this, and methyl and methyl. Okay, so you would add Br here, correct? Let's say you added Br here and H here. It does not make any difference because both of them are symmetrical here. So therefore, we could have this as, you know, this way with Br here, correct? How many isomeric products? Because this is a chiral center and this is a chiral center. You'll have total four isomeric products. How many fractional distillations we can get? Okay, we can get only two because out of these four, right? Out of these four, both of them are enantiomeric mixtures. So at this chiral center, when you'll have one enantiomer. This one will have one enantiomeric pair. So only two fractions are possible. So X plus Y is how much? 6. How many alkenes on catalytic hydrogenation give isopentane as product? Okay, so what is isopentane? This is isopentane, everybody. So we need to make all the possible alkenes. Okay, so now this was a JE question before where it is supposed to be only monoalkene mentioned, but they have not mentioned because it makes us resume. It makes it assume that there might be multiple double bonds. Okay, so only think in terms of mono double bonds and check out how many number of pi bonds you can make it. So here you can see I can make one pi bond here. I can make one pi bond here. I can make one pi bond here. But none of them have geometrical isomers. So answer is only 3. How many alkenes on acid hydration, 2-methyl, 2,3-dimethyl, 2-butanol will be produced? How many alkenes on acid hydration produce butanol like this? OH and 2 and 3. This is what is to be produced here. So now let me put double bond so that we can get this product here. So where all I can put this double bond? I can put, because this is how the structure is, I can put one double bond here or I can put one double bond here. Okay. Or I can put one. So I think these are only two, sorry, because rest all are repeated. Please check. From here only, if you hydrolyze that, right, you'll get these two products will lead to the same product. Okay. So in the case of 23, we can have only this 2, 3. Did I miss anything? Will be produced one more. 2, 3-dimethyl butanol. 2-butanol. Okay. So structure is correct. Double bond here. H plus and OH will be added. Here and H plus and OH minus will be added. Yeah, this one will also come. Sorry. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah, this one will also come. See why? Because in this case, migration can happen. See, first protonation can happen here. H will get added, positive charge will come, and then migration will happen, and then positive charge will come here, and thereafter on hydrolysis, you will get OH. So check everybody. This is compound 1, this is compound 2, and this is compound 3. So these three are the isomers which can lead to the same product. So answer is 3. Please check 24. Concentrated H2SO4, number of isomeric alkenes. Okay. So on this position already we can have double bond here or double bond here. Only these two are the possible forms. And here we can have cis and trans, here nothing. So total 3 we can have. Fractional distillation will give you 2. So 3 plus 2 is 5. Correct? But fractional distillations are three only, no? Because cis and trans can also be separated out. So six. Okay, so 3 plus 3 is 6. Next, 25. Consider the following reaction. Brine solution. Very important case here. When you have bromine water, Br plus is electrophile. But what are all the nucleophiles? Water is a nucleophile. Br minus is nucleophile. Because there is a brine, brine is NaCl, aqueous NaCl. So Cl minus is also a nucleophile. So there are three nucleophiles that will be present. All three products will come. And you know that nucleophile attach on more substituted kind. So this is X. So these three could be X. And here Br will be present. Br will be always on that secondary position. Okay. So based on that, check out the options here. So 2,3 dibromo 2-methyl butane, which is true. Bromine can come. Next, 2,3 dichloro. Dichloro will not come, so this is incorrect. 2-chloro 3-bromo 2-methyl butane. That is correct. That can come. 3-bromo 3-bromo 2-methyl 2-butanol. That is also correct. So these three can come. Correct options here. Boiling point. Now notice you need to check out the uh, dipole moment. Here you can see the dipole moment goes like this. So which means it is getting added. So we can say that dipole moment of trans in this case is greater than dipole moment of cis. So more the dipole moment, more is a boiling point. Next, melting point. Melting point only depends on the geometry. More symmetrical it is, more is a melting point. And always trans is greater than cis. So that is correct. Reactivity towards HBr. Now, here the carbocation is more stable. Here the carbocation is unstable. So this is an incorrect order. Boiling point. Boiling point, generally speaking, cis is greater than trans because in this case, mu is greater than mu here. So D is correct. So A, B, D. Next, check out some statements regarding the following reaction are given below. Okay. If this is a compound, I use sodium in liquid ammonia. So first I will get a trans molecule. So this is the trans molecule, use Birch reduction. From trans towards Q1, what do we get? Because it is an anti-addition, it will get erythro. So we'll get Br here, methyl, methyl here, H and H here. With DT and nickel, it is going to be forming 3O. So D and D will be here, methyl and methyl will be here. And see in this erythro, this is plane of symmetry passing through it. So that means it makes it, this is meso. While here it will have plus and minus. So that makes it racemic mixture. So first identify the idea about Q1, P, Q1 and Q2. Okay. Now go for the options. P is a trans alkene. True. Q1 is a pure compound and optically inactive due to internal compensation. True. Okay. And next, P1 to Q1, P1 to Q1 here. Okay. Conversion of step, the Br2 adds on P in a syn manner. So it is not adding in a syn manner. And the intermediate formed is a cyclic bromonium ion. Okay. Now listen up. When he using the word syn manner, a lot of students get confused that sir syn means the first attack or the overall attack. Since he did not mention that, you always consider it as overall attack. Overall attack is anti, so that is incorrect. So this C is incorrect. Next, Q2 is a binary mixture uh, and it is optically inactive due to external composition. That is also true. Done. Next, 28. Identify relation between P and Q. So first one is oxymercuration, demercuration. So P, what you will get is OH here. In the second case, what we get is OH here. Okay. So P and Q are, constitutional isomers because their position is different. Okay. And constitutional isomers are also called as structural isomers. Incorrect order of the rate of electrophilic addition with HBr. Just check out the most stable carbocation. Here is a most stable carbocation. Then next is this one. Next is this one. The least is this one. So 1, 3, 2, 4. Okay. So one is the most reactive one. So 4 and 1. Sorry, incorrect we need to find. So I was correct. Trying to figure out correct one. Sorry. This is incorrect. This is also incorrect. In fact, all of them are incorrect orders. Next. Alcoholic KOH. Alcoholic KOH will give you elimination here. So for that, you better check the chair form of it. In the chair form, make sure the chlorine is axial first. And then, since it is opposite, so methyl is also axial. And you know that we need to get an anti-periplanar between hydrogen and chlorine, which is not present here. So in that case, the major product will be forming on the other side only, like this. Okay. So if you write this down, so basically we will have methyl like this and double bond is formed here. So this is the major product A. So A is a Hoffman product, which is true. A is Shezhev product, wrong. It involves free carbocation as an intermediate form. Okay. Alcoholic KOH does not go any carbocation formation. Next, A exhibits a geometrical isomerization, which is false because A exhibits, because now it has a chiral center, it exhibits optical isomorphism. Okay. 31. Number of fractions obtained after fractional distillation of the mixture is. Again, Br to brine solution is been added. Please check it out. Like this, we have deuterium fixed here. Okay. And bromine is also fixed here. Now we need to just add the other groups. Okay. I'll write the other groups here. So 1, we can have OH here, correct? This way with a chiral center. 1, we can have Br here with a chiral center. 1, we can have Cl here with a chiral center. Done. Now notice carefully, this is a chiral center, so that makes it as 2 isomers. Here also 2 isomers. Here also 2 isomers. So in total 6, but all of them are diastereomers. Reason being, there is already an existing fixed chiral center present. So number of fractions obtained after distillation of the product is, because all of them are diastereomers, they all will be separated out. So answer should be 6. The total number of alkenes possible by dehydrobromination of 3-bromo, 3-cyclopentyl hexane using alcoholic KOHs. 3-bromo, 3-cyclopentyl hexane. So we have hexane, cyclopentyl here. Three bromo, 3. So Br here. Sorry. I thought cyclohexane. My mistake. 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6. And on third position, we have bromine also. And we have cyclopentyl also. This way. So now, if I make the elimination, what are all the products I'll get? Please check carefully. This side we can get a double bond. And this is one product. Or this side I'll get a double bond. This is one product. Or this side I'll get a double bond. This is another product. So these are the possible products, everybody. In this case, we can have cis and trans, so you'll count it as 2. Here, there are no cis and trans, you'll count it as 1. Here again, we have cis and trans, you'll count it as 2. So total, how many we can get? 5. Next one. If the ratio of number of hybrid orbitals to pure orbitals in the product is x is to y. Okay. This case we have done. This will always end up getting benzene. So we know that we'll get this as benzene. So in the benzene, if number of hybrid orbitals to pure orbitals is x is to y. So x is about hybrid orbitals and Y is about pure orbitals. Correct? So how many hybrid orbitals do we have here? So check out. Every carbon possesses three because you'll have sp2 here. So these three are the hybrid orbitals. Correct? So total six carbons into three. So that makes it 18 hybridized orbitals. Hybrid orbitals. Okay. Why is that so? Because every carbon will have sp2 form. So which means each sp2, one sp2 here, one sp2 here, and one sp2 here. And next one is pure orbitals. How many pure orbitals we have? Each carbon will have one pure orbital here like this, which will make a pi bond on it. Okay. So therefore, pure orbitals. So when it comes to pure orbitals, that is going to be 6. So basically we have 18 by 6. So that makes it 3. 18 by 6 makes it 3. Okay. Let's check. Wait, answer given is 1.5, I guess. Let me just check if at all I made any mistake. Number of hybrid orbitals to pure orbitals is. Oh yeah, sorry. Hydrogens are also present. I forgot to answer that. Outside hydrogen is also pure orbitals here. This side. Hydrogen are in pure orbital. This is S, 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 and S. So total we have 6 plus 6. So total 12. So 18 by 12. Clear? So that makes it 1.5. Next. Notice this case. Number of possible alkenes is. So here we have tert-butyl, chlorine here. So this first thing we will make is make a carbocation, and carbocation will undergo rearrangement to get a positive charge here, right? And now you have to check out all the possible alkenes. So in the first case, the possible alkene is only one, which is this one. Second case, after rearrangement, we can get possible alkene as this one and another possible alkene as this one. So these are the three alkenes which we can get. Okay. So how many we are getting? Only three. Next. Alcoholic KOH, what is the pure form here in 35? Okay. All chlorines are up here. So one chlorine up and hydrogen down here. So I can use that. So as you use it, so we will get double bond here, one chlorine will be left. Double bond here, one chlorine will be left. Double bond here, one chlorine will be left. So that is a major product. Okay. So add the total. Total is coming out to be 259.5. So that is a molar mass. Sorry, not 259.5. I mean, I have to check out the Q also here. So now, if you take it, magnesium excess here, okay. So magnesium would also take away chlorine and chlorine here to make a double bond here. So these two chlorines will be out, these two chlorines will be out, these two chlorines will be out. So that makes it benzene. So in this case, benzene plus 3 moles of MgCl2. So the sum of these molar masses is coming out to be 259.5, everyone. Okay. Check out 36. Trans 2 pentene reacts with Br2CCl2. Trans 2 pentene this way and react with Br2. So what is the product I will get? I will get one Br here and one Br here, both being chiral centers. Correct? You will get two products because they are anti, because there is an anti-addition. So next one is about cis-2-butene. Right? So like this one, two. Cis-2-butene, when you add with this one, so here also you'll get two bromines, right? And since there is erythroform here and no mesoform, here also you'll get two products. Right? So how many total? X plus Y is 4. Uh, in Fisher form, if at all I have to write it, everybody, this is trans making an anti is erythro. So Br and Br, methyl here, ethyl here, and hydrogen. In the second case, we are using cis with an anti here. So that means it is threoform. So Br and Br will be opposite. So methyl and ethyl will be formed here. So this is the product formation. All good, everybody? Right, let's go to the next assignment. Day 2 assignment 1. This one. An organic compound reaction with ozone followed by zinc and water gives. Please read it, everybody. So we are getting this as a final product. The compound may be. Okay. So one could be in an open chain form, one could be in a closed chain form. So imagine if these two are closed. So 1, 2, 3, 4. So it is like a four-membered ring here, like this. And it has an ethyl here and ethyl here. This is one possibility. Or the other possibility is here there is a bond broken, here there is a bond broken, right? Then you can get a product here. So which appears to be B and D. Please check. These two are the cases. Next, which of the following compounds on treatment with hot KMnO4 followed by acidification gives butanoic acid as one of the products? Chalo, we can see oct4-ene. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4 here. So if you break the bond here, so what is the ring size now? 1, 2, 3, 4. 1, 2, 3, 4. So what are we getting? 2 moles of butanoic acid. 2 moles of butanoic acid. Right? So A is correct. 3 methyl hept 3-ene. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3. 3 we have 3-ene and we have methylene here like this. So if I break it here, so what do I get? 1, 2, 3, 4. So this is also getting butanoic acid. Next. 2, 3 dimethyl hep 3-ene. So here we have 1, 2, 3, 4, 5, 6 double bond and 2 and 3 here. Correct. So this is how it is present. So in that case also if you break it down, so we will still get butanoic acid as one of the cases. Oct2-ene. If you have oct2-ene, we will not be able to get the butanoic acid form. So what is that? ABC. 22. NBS, possible number of stereoisomers is. Okay. This I explained last class. I mean, when we discussed isomerization, the trick I told you is write down all the possible radical forms here. So you can see these two are the possible radical forms. By the way, this side is same as this side, so I'm not writing the again. So then write the resonating structure. So double bond out dot here. Correct. So this is one possibility. And double bond here. And this one is one possibility. And its resonating structure, double bond here, dot here. That is another possibility. So for this, we will get double bond here and Br here. For this, we will get double bond here and Br here, which is making a chiral center. Next. For this, also double bond here and Br here, which also make it as chiral center. So which is 2. Okay. One second, did I miss out on anything? Getting bromine on that side is 2. And here, bromine coming on this side and that side is same. These two are same. So we are getting not many products. Dot here, dot here. Oh yeah, these three positions are different. My mistake. Sorry. This position is close to methyl. This position is different. So I had to take that position also, not this one. These are creating same positions. So I didn't take this part. Check out here, double bond and dot here. And after that, resonance stabilized, another dot here. So with respect to this, if at all I put the double bond here, I'll get bromine on this position. And with respect to this, if at all I put bromine here, I'll get this position. So here we'll get two. Chiral center is there. Here we will get two. Okay. So here we got two and here we got one. So how many we have total? 8 plus 1, 9. So 9 possible stereoisomers. Please check. Next, which of the following will react with sodium metal? Okay, we need to take the terminal alkyne. This is terminal alkyne, terminal alkyne. Okay, one in, one all. Even if you have an alcohol, that will anyway give sodium metal test. So ACD. 2-butyne, H2 by palladium barium sulfate here. So since it is 2-butyne, it will give you 2-butene. Okay, and N2D2 will make a syn addition. So on cis molecule, if I make a syn addition, what should I get? I will get an erythro. So which means I'll get D and D, H and H, methyl and methyl. So what is this one? A mesoform. This is the final product. So A is a cis isomer and B is optically inactive. So these two are the correct options. 25. Which of the following reactions forward reaction is favorable? Okay, so C minus can take H plus from here. Okay, so because this acid, I mean this alcohol is more acidic than this one, the reaction is feasible. The second reaction is also feasible. Okay, why? Because NH2 minus will be taking H plus. It will give ammonia, and ammonia pK value is 38, which is feasible, and alkynes are generally 25. And here this is not feasible because it forms water, and water's pK value is 15.7. And with sodium, hydrogen gas will come. Hydrogen gas pK value is 39. So this is also possible. So A possible, A is possible, B is possible, D is possible. Please check. Next, what is this reaction? First, just the other day I explained you the same question. I remember in the class I explained you the very similar question here. So A, what is the A form? I told you it will form a dimer in the when you have a neutral medium. So dimer includes, okay. So CH triple bond C, then we have CH double bond CH2. So this is compound A. And uh, from here, you're using C2H5 MgBr. Okay. C2H5 MgBr is a strong base that will take H plus from here. So that will create C triple bond C, CH double bond CH2 minus. And this minus will attack on the ethyl group. So we'll get Et, then C triple bond C, CH double bond CH2. So this is product B, everyone. And this A, when you perform ozonolysis, this also I told you that if you make ozonolysis, double bond is the one which will break. So it will break and you'll get CH triple bond C, CH double bond O plus HCHO. Okay. and this is compound C, and that making a Kuchros reaction. So if you make a Kuchros reaction, what do I get? I will get this aldehyde is anyway present here, and this side I will get an enol form, and that enol will convert into a keto form. So we will get this as double bond O, double bond O, H, and H. So this is the product form. So what is the double bond equivalent of B? How much is the double bond equivalent? 2 plus 1, 3. So answer is 3. Second, sp2 carbon atom product D is formed. So D, achha, how many sp2 carbons are there? 2. 2 sp2 carbons are there. That's it. Check. All good? See the next question. Mg2C3, Mg2C3 on hydrolysis will give you CH triple bond C and CH3. Propine, you will get propine. And NaNH2 will take H plus away and C minus will attack on methyl. So you will get this as CH3, C triple bond C, CH3. That is Q. Red hot iron tube. This also we discussed that you will get all hexyl group on it like this. Hexamethyl benzene. Okay. So P when you perform with here, where is that? 100% yield, but you are reacting with 40% H2SO4 and Hg2SO4. So that is, Kuchros reaction. So Kuchros reaction will convert this into keto form. So this is S, compound S. Okay. So all you need to do is calculate the mass of X and Y. Just check out the percentage yields. Between Q and R, you need to make sure the reaction is perfectly balanced, because this is how the reaction would be. This one, 3 moles of it is converting into 1 mole of this one. So while making the stoichiometry, you need to take care carefully. That's all. So calculating this X and R, I remember I'm getting values as 6.75 and 29. These are the values we are getting. Okay. Next. Bayes reagent is an indication test for unsaturation. It gives diols with alkanes, correct? And number of isomers possible in X and change in oxidation state is Y. I think this similar question I told you already. We have OH and OH. Both will be on the same side like this. And this and its mirror image will make it two possible isomers. Okay. And manganese is changing from MnO4 minus all the way to MnO2. So which plus 7 to plus 4, which means 3 electrons transfer. So x plus 5, x plus y is 5. How many of the following molecules give symmetrical diols? Okay. Gives symmetrical diols. Symmetrical diols means, okay. So basically, check out here. 1, 2, we have 1, 2, 3, 4, 5. So on 2-pentene, we will get this as OH, okay, and OH. So this is not symmetrical. Symmetrical as in we should have something like a mesoform. So that is not what you are getting. In the second case, 2,3-dimethyl 2-butane. We have 2,3-dimethyl 2-butane, correct? So in this case, you will get a symmetrical form. Okay, symmetrical diols. Yeah. Next, 3-heptene. 1, 2, 3, 4, 5, 6. 3, 6, 7. So 3-heptene like this. So if you remove that, we will get this as OH and OH. So this is not forming a symmetrical diols. Next, fourth one. Trimethyl ethylene. Trimethyl ethylene. Okay. So we have CH double bond CH and we have trimethyl. So basically we have 3 methyl groups here and ethylene group. So basically C and C, 1, 2, and 3. So methyl here, methyl here, methyl here, double bond, H2 here. So this way. Right? So this is not going to give you symmetrical form. Okay. Next. Tetramethyl ethylene. Tetramethyl ethylene is same case. Earlier we did it. That is going to give you symmetrical form. 4-octene. 4-octene. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So here we have double bond. Yes. Now if you put OH and OH here, removing that, so now it is symmetrical. On both ends it is same. So therefore, yes, this will also give 3,4 dimethyl 1 methyl 3 hexene. So this is hexene here. Sorry, 1, 2, 3, 4, 5, 6. So 3, 4 dimethyl, 3 and 4 dimethyl, and 1, 2, 3. So 3 hexene here. Correct. Dimethyl 3 hexene. Yeah. So if you break it down here, here also we'll get a symmetrical diol. So this one will also come. So how many we can get? Total 4. Clear? Actually, 2 and 5 are same only. So, that's why the key change was done for this case. So 3 or 4. Next question is addition of carbene on alkene gives cyclic structure like this. Okay, which is fine. And what will be the major product? A is a major product. And yeah, we need to figure out which one is major product. See, listen up here in this case. So first what would happen? When you have this case here, so first we will make this into CClBr as the carbene form, because O minus will take away H plus. Thereafter, Br is a good leaving group, so that will go away, and this is the carbene which is formed. And this carbene is the one which will get added onto this one like this. So CCl and Br with this way. Now what happens? Br is being a good leaving group. It will undergo elimination via expansion. So why by expansion here, now you'll have a 6-membered ring, correct? So with chlorine here, right? And then if this is 1, 2, 3, 4. So we have this as 1, 2, 3, 4. Between 3 and 4, we have a double bond. And 5, 6. So 5, 6. 6 we have a positive charge here, this way. Okay. But already there is a double bond which was existing. Okay, beforehand there was a double bond existing. Sorry, here we had 1, 2. This got connected here. 6 and so we have 1, 2. 2 is here. Yeah. So now between 1 and 2, we got a new double bond. This one, 1, 2, 3, 4. And that positive charge will, the base will take H plus away and gives this into a positive charge like this. So what do we get? Chlorobenzene. So B is the major product. Next one, C5H10 plus CHBr3. Number of addition products on alkene, excluding stereoisomers. Okay, so that means there is an open chain alkene here. See, how many alkenes we can make? So I can make one alkene here. I can make one alkene here. I can change this into this form here and make double bond here. And I can make one double bond here. And I can make one double bond here. These are the types of double bonds we can get. So on all of these double bonds, now I can make an addition of those compounds. So if I make an addition here, so what are all the products you can get here? So C, you'll get this as C, Cl and Br like this. We can get the same thing here also. We'll get this as C, Cl and Br. Same way here also. Remove this part. We'll get CClBr. So at all these positions, we can get ClBr. So that is the question asked, that how many number of products you can get in this case. Like this, Br and Cl. Okay. Sorry. Here. Where did I not add? Here I didn't add. Like this, Cl and Br. Done. So how many we got? Total 5 products. So answer is 5. Excluding stereo, it is 5. Catalytic hydrogenation of unsaturated hydrocarbons liberate heat energy. Which of the following liberate most of the heat energy? Okay. Check out based on number of alpha hydrogens first. Here alpha hydrogens are 2. Alpha hydrogens are 6. Alpha hydrogens are 6 here. Okay. Alpha hydrogens are 3 here. So between 6 and 6, we learned that isobutylene will give, uh, less amount of heat compared to this one in a cis form. Correct. So when it comes to 34, the order will be almost B and C will be similar, then D, then A. So A will be the least stable. So that means that will release the most amount of energy. So since it's single correct, you don't have to worry about B and C's order. Okay. Discussed a similar question. Okay. So here we will get a transform here like this. Correct. So this is the ethyl what you need to write, which is option D. First, X moles to form, first NaNH2 is forming here. So that means we'll get C triple bond C minus and minus here. And both sides we are getting ethyl. So C triple bond C and this one. What is the value of X? X is how many moles we took? We got this as, one hydrogen from here, one hydrogen from here. Correct? Gone. And again, one more hydrogen, one more hydrogen. So total how many moles we used? 4 moles. So we use 4 moles of NaNH2 to get this product. Next, what is the position of bromine in the parent chain? So look into it. This is like an 1-2 addition, 1-4 addition case, like this. So we need to check out the most stable carbon here because there is no temperature mentioned. So you'll go always with thermodynamic stability. So H here, positive charge. This is the most stable double bond. And on the most stable double bond, then, sorry, first you need to write that carbocation and then make a more stable alkene here by making the resonance. So then you make an addition of Br. So this is the final product. This is a thermodynamic product. Okay. Now when you make the IUPAC numbering, you start from here 1, 2, 3, 4, 5. So bromine is on which position? 4th position. Please check. This is how we need to go. First make a stable carbocation, then make a stable alkene. Most stable alkene is thermodynamic product. Calculate the number of isomers possible with the molecular formula C6H10 to give white precipitate with Tollens reagent. Okay. The molecular formula C6H10 to give white precipitate with Tollens reagent. See, white precipitate with Tollens reagent is AgNH3 twice plus. This is Tollens reagent. Tollens reagent will give white PPT whenever there is a terminal alkyne. So when you react with this one, I'll get this as RC triple bond C minus and Ag plus. This is what is going to be formed. This is white PPT. I forgot to recall this one for you. So if you remember, by chance, if you have Cu2Cl2 in the presence of NH4OH, In that case, you will have copper precipitate here, which is red color PPT. Red PPT. So in basic medium, it will give you red PPT. So anyways, question is number of isomers possible with this formula. So basically, I need to get a terminal alkyne. Everybody check into this. So we have one, I'll start from here. So you can see 1, 2, 3, 4, 5, 6. So terminal position is this one. Now I'll just simply keep adding out the uh, branches to it. So like this, these are the branches which I could add. And then I can have two more branches this time. So one methyl and methyl branch here. Correct. So only these are possible ones. But here there is a chiral center also that makes it 2, 1, 1 and 1. So total 5. So 5 isomers including stereoisomers. Please check. All okay, guys? Done, guys. Okay. So I think we discussed how many papers we discussed so far? Three of them. So tomorrow I'll discuss rest of the papers. Sorry. That includes assignment 2. Please make sure that you finish this part. Okay. Day 2 assignment 2. Please check out if you have got this assignment or not. Otherwise, I'll ask sir to give it to you. This is the next assignment. And then this one part day 3 day 3 first day, I mean assignment 1, and day 3 assignment 2, this. Okay, so these three you have to finish it. If you get time today, please complete this part. Otherwise, tomorrow I'll discuss all the important questions in this case. Then I'll give you two tests. Okay, so if you finish that, I think the preparation will be good enough. Right, guys? I'll Okay. Right, guys. Thank you.